Go ahead and record. I'm going to share my screen. Today we're going to be talking about trigonometric identities. And so some of you have done some of these identities in the past in your Algebra 2 class. Some of these we've already talked about, to be quite honest. Like we've talked about several of these already, but we're going to go through their names and then how they work for each of these. So go ahead and copy this slide down. We're talking about chapter 7, which is trigonometric identities. I graded your chapter 5, 6 test. Some of you did well. Some of you are not showing the work that you need to show. Some of you are continuing to forget thetas or x's. Most of you did way better on this one than you did on the last one, even though there was additional topics in there. So at some point, just go back and look through my feedback. Some of you clearly didn't look at my feedback on the first one, and then I put the same question on that second test, and then you made the exact same mistake. So always check my feedback, because sometimes I'll repeat questions, and if you haven't looked at it, you're going to still miss them. So, okay, so reciprocal identities. Some of you guys accidentally call these inverse. Reciprocal and inverse mean different things, right? So we talked about inverse trig last week. Inverse trig means we're actually swapping out the input and the output. So instead of like cosine of an angle equals the x coordinate, what we would be doing would be cosine inverse of an x coordinate gives us an angle. That's the idea of cosine versus cosine inverse. So when I'm talking about a reciprocal, the thing I'm talking about instead is 1 over the related function. So cosine is the same as 1 over secant of theta. Again, there needs to be thetas on all of these. If you just write COS or SEC, that's wrong. Okay. And secant is therefore 1 over cosine of theta. Sine is 1 over cosecant of theta. Several of you are messing these up. Some of you think cosine goes with cosecant and sine goes with secant. That would be nice if that was true, if the S went with the S, but it does not. Okay, cosine goes with secant, sine goes with cosecant. So make sure you haven't memorized that incorrectly. And then cosecant is 1 over sine, tangent is 1 over cotangent, and cotangent is 1 over tangent. Hopefully you're going to have a couple nice sheets in your notebook that have all these trig identities so you can kind of reference back to them as we go through studying these next couple weeks for this chapter. So this is a good one to have, which is the reciprocal identity. Okay. If I ask you to write the reciprocal identity for tangent, you need to be writing 1 over cotangent. So knowing the name of it is actually important too. Okay, any questions on this before we move on? All right, our next one is called our quotient identities. So our quotient is usually used for division, and that's exactly what we mean here. So we mean division. So tangent of theta, what we know this is that tangent is the same as sine of theta over cosine of theta. And then cotangent, since cotangent is the reciprocal of tangent, you would just flip it over, right? So instead you'd have the cosine on the top, cosine of theta, over sine of theta. Most people only know these quotient identities, and this is generally fine because I can always write everything in terms of sine or cosine. But there's actually additional identities. So for example, if I were to use the reciprocals, I could come up with more quotient identities, right? So sine of theta divided by cosine of theta, please write this down, is the same as sine of theta times 1 over cosine. Sometimes it's helpful, instead of having it as one fraction, to split it up as multiplication to be able to see what's happening here. Right? So we have sine of theta times 1 over cosine theta. That's exactly the same as what I had above. So it's the same as tangent of theta. Still tangent, right? Everybody hopefully sees that that's the same. Sine of theta over cosine theta is the same as sine of theta times 1 over cosine. Okay. Now, if I use the reciprocal for sine, that would be cosecant of theta, but it doesn't stay on the top, right? Cosecant, if I want to make it equal to sine, is 1 over cosecant. That would be the same as sine of theta. And since I have a 1 over cosine, if I use the reciprocal identity there, that would be equal to secant of theta. Does everybody see how I got to those two different values? that sine is the same as 1 over cosecant, and 1 over cosine is the same as secant. So another thing that tangent is equal to is actually secant of theta over cosecant of theta. Using my reciprocal identities, I can come up with that. Which means cotangent, I would just flip it. So we could go through that process again, or we could just recognize this one's going to be cosecant of theta over secant of theta. This chapter in dealing with trig identities is kind of like solving puzzles. So it's kind of like taking what you're given, rewriting it, and putting out something else, potentially something more simple. Okay, but it's like the same part of your brain that's going to solve a puzzle. That's kind of what we're doing in this chapter. We're taking all the information we have and we're kind of rewriting stuff and solving puzzles. Are there any questions on quotient identities? The most important ones are the first ones we talked about. I just wanted to clarify that those could be equal to additional identities. Okay. All right, let's move on to the next one. Now we're going to talk about even and odd identities. I'm guessing the rest of this is going to be brand new to everybody. If you guys remember talking about even and odd functions, when we talked about even and odd functions, what we said was for an even function, f of negative x is equal to f of x. This was a long time ago we talked about this, right? F of negative x is equal to f of x. That meant if I plugged in a negative x into a function and I got exactly the same thing as when I plugged in x, that it was even, right? So if I started with like x squared and I plugged in negative x for x, so I would get negative x quantity squared. That simplifies just down to x squared, which is exactly the same as if you just plugged in a regular x. If it's an odd function, when I plug in the negative x, this time I don't get exactly the same thing as what I started with. What do I get? Does anyone remember what you get?
Negative f of x.
Negative f of x. So I get like literally the exact same thing, just times -1, right? Or all of the signs switched. Hopefully you guys remember doing that. Again, all this stuff will be on your final exam. So it's good that we're kind of coming back to some of these topics. So that's how it works with general even and odd. We also have even and odd functions for trig. Now, cosine of negative x is an even function. Meaning if I plug in a negative angle, it's going to give me exactly the same thing as if I plugged in the positive angle. Okay, cosine is an even function. Meaning if I have something like cosine of negative pi over 4, that's going to be literally exactly the same as what I would get if I plugged in a positive pi over 4, no matter what the angle is. If I plug in a negative value, I'm going to get exactly the same thing as if I plugged in the positive value, which you can even imagine that, right? That would be for pi over 4, that would be like the first quadrant or the negative first quadrant. You would get the same value. You would get that positive rad 2 over 2 in both of those for cosine, right? You plug in that negative value, you still get positive rad 2 over 2. But it works for any angle, even outside of that first quadrant, okay? Sine and tangent went together when we were talking about inverse trig, right? They have the same restrictions. Sine and tangent go together a lot, actually. These are both odd functions. So they have the same restrictions, and they're both odd. Meaning, if I have sine of negative x, what do you think I would get since it's odd?
Negative sine x.
Negative sine of x, exactly right. So I would get a negative sine of x. Meaning, for example, if I wanted to know what sine of negative pi over 4 is, it's going to be exactly the same as sine of pi over 4, but times -1. Right? And that should make sense. Like sine of negative pi over 4, that puts me in the fourth quadrant, right? Or that negative first quadrant where y is negative. That's exactly the same number, it's just negative, as if I did sine of regular pi over 4. Okay, so you can visualize some of those examples, and that can help you remember which one is even and which one is odd. Tangent is also odd, meaning tangent of negative x is the same as negative tangent of x. Now, since cosine was even, its reciprocal is also even. So secant of negative x is just the same as secant of positive x. So since cosine was even, its reciprocal is also even. And that logic goes also with the reciprocals of sine and tangents. So these are also odd. So cosecant of negative x is the same as negative cosecant of regular x. Cotangent of negative x is the same as negative cotangent of regular x. Any questions on these so far? Please ask if you have a question or how this works. We're going to do some examples together, but ask if you've got a question. Okay, we're going to move on. Hopefully you guys have this written down. I don't want to go too quickly, but I want to make sure we get through all of this. Okay. The next thing we're going to talk about is an identity called the cofunction identity. This one is really strange. If you want to just take a second and copy down what I have on the screen right now, that'll make it a little easier to talk about. So I'm going to give you about a minute. You can go ahead and copy all that down. It is important that you have it in the right order. So it has to be pi over 2 minus x. It's not the same as x minus pi over 2. So it should be pi over 2 minus x for all of these. And again, we're working in radians almost exclusively. If it was in degrees, it would be 90 degrees minus x. But again, we'll work almost exclusively in radians, pi over 2 minus x. I know this is a lot of information to cover here. We'll do some examples that'll make it a little easier, but I just wanted all of this to be in your notebook. Okay, I want to talk about what each of these finds, and then we'll actually fill this in. So if I gave you sine of x, and we were to graph that function, right? You should feel somewhat comfortable with this now. Several of you did very good on all the amplitude, phase shift, vertical shift, all that stuff. But sine of x, sine of 0 is 0. Let's fill in some of these values. Pi over 2, pi, 3 pi over 2, and 2 pi. Myself a little extra room. Right, sine of pi over 2, well, that value is 1. That would be up here. Sine of pi is 0. Sine of 3 pi over 2 is -1. Sine of 2 pi is 0, and it would just continue from there. So I would get a graph that looks something like this. And I would encourage you to write this down. This will make the cofunction make a little more sense. So I get this graph. Obviously, it keeps going, right? It continues to oscillate, but we're just going to draw that portion of it. If I gave you sine of pi over 2 minus x, and I asked you to identify the transformations that happen there, this is a little bit confusing because usually, like if it was x minus pi over 2, if that's what I gave you instead, if I gave you sine of x minus pi over 2, you'd probably know how that moved. Does anyone know how that one moves? Of x minus pi over 2? Has a transformation.
It would be, wouldn't it be right pi over 2?
Exactly right. So it would go right by pi over 2, right? That's what this graph would do. So you might write that down because that is helpful to know. But that's not what I have. I have sine of pi over 2 minus x. So what we did is we did something, if you guys remember, when we had like, I think e to the x's or ln of x's, where we factored out a -1. So we made it like sine of negative. I factored that out inside of the parentheses. So if I take out a negative from both of those things, what I would end up having inside this new parentheses would be x minus pi over 2, right? I could distribute that negative here and I would get back to the same thing as the one above. So I'd have a negative x and a positive pi over 2. So if I take out that negative, I have sine of negative parentheses x minus pi over 2. Well, this still means right by pi over 2. What does this one mean though? What does that negative inside of the parentheses do? Does anyone remember? This was a little bit of a harder transformation to remember. What's that do?
Don't we flip over the x-axis?
So you don't flip over the x-axis. That would be if there was a negative out in front, right?
With the y then.
This would be the y-axis. So you'd flip it over the y-axis. So really what this transformation is a flip over the y-axis and then a shift right by pi over 2. Or since sine is an odd function, since sine is odd, sine of negative anything is the same as negative sine of that something. Right? So actually these things are equal to one another for sine, just because sine is an odd function, right? But exactly what you said a second ago is correct, that this is a flip over the y-axis. So let's think about what happens when I do that. So if I took that and I flipped it over the y-axis, then I have this hump is right over here. So it goes like this. And then this hump is even farther over this way. And it's all those negative values, right? So that would be what that graph would look like with just the flip. So again, this would be like negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. Okay, so that's the flip over the y-axis. And then I would still move it to the right by pi over 2. So moving it to the right by pi over 2 means each of these dots would move pi over 2 to the right. So this dot moves this way. This dot moves this way, right? This one moves over here. This one moves over here. And then this one would be over here at pi over 2. So what I'd end up getting would be this graph. And then this graph would just keep going, right? It would go like this, and it would keep going forever and ever and ever. The yellow graph is the graph of sine of pi over 2 minus x. But it is also the same as what graph? Does anyone know what that graph is, the yellow one?
Cosine.
It's the exact same as just normal cosine. So what we mean by a cofunction is if I were to take sine and I were to flip it and then shift it to the right by pi over 2, I would just end up getting cosine. So I would end up with sine of pi over 2, I end up just getting the graph of cosine. What's pretty cool, and we're not going to go through all of these, I'm just going to explain them, is if I did the same thing with cosine, so if I took cosine, I flipped it over the y-axis, and then I shifted it to the right by pi over 2, we actually just perfectly end up with the graph of sine. So those graphs are just flips and translations of each other, right? If I took it and I flipped it and I moved it to the right, if I start with cosine, I get sine. If I start with sine, I get cosine. Okay, and then the same thing happens with these next sets. So these kind of are a set that go together, cosine and sine. If I have secant of pi over 2 minus x, what I end up is with the graph of cosecant of x. And if I start with cosecant of pi over 2 minus x, I end up with the graph of secant of x. This works for all of these cofunctions. And then finally for tangent and cotangent, those go together. Oops, probably shouldn't have written that right there. Cotangent and tangent. Okay, you don't need to know how to graph all of those right now. I know we mostly just know how to graph sine and cosine. I just wanted to explain to you how this thing works. All it is saying is that for all of these functions, if I flip them and then shift them to the right by pi over 2, I get the cofunction identity, which is sine for cosine or cosine for sine or etc. Any questions on any of those? Okay, we have one more big one to talk about. And this one might be one that you guys have seen before in Algebra 2. You've probably seen the most basic version. We're going to talk through how to come up with all of these and really what it means. So Pythagorean is our last trig identity that we're going to talk about. And I would like you to draw the little picture I have there. So I've got a little triangle in the first quadrant, and it doesn't matter what angle it is. I've just called the angle theta. It's a right triangle. And I've identified the X and the Y as the coordinate up top there. Okay. So the X and the Y is the coordinate on top. Thanks, Harrison. Okay, so we have this triangle drawn. Please make sure you write Pythagorean. This is our last identity we're going to talk about. Most of you know Pythagorean theorem because we've been doing it a lot when we've been solving these triangles, right? What we've been doing is we've been doing x squared plus y squared equals r squared. We're not really using a, b's, and c's anymore. We're talking about our Roxy triangle. So in general, like this is our r, this is our x, this is our y, and we are able to solve that triangle using x squared plus y squared equals r squared. Now, when we're on our unit circle, we know something very specific will always be true, which is that our r is always equal to what value on our unit circle? What's our r always equal to? Ty, say it out loud.
1.
Correct. Our r is always equal to 1. Okay. And we know something else. The x and the y coordinate actually represent trig functions. So what's the x coordinate represent? Someone else. Do I need my spinner? Can someone just go?
It's cosine.
Cosine. Perfect. Now I'm going to write cosine of theta. And then our y coordinate is our sine of theta. Right? Everyone feels pretty comfortable with that. That's what we've been talking about. Our x is our cosine. That means like the bottom sign here is cosine. The side over here is sine of theta. And they can be negative or positive depending on what quadrant we're in. Well, that's still a right triangle. And so our Pythag is still going to apply to this exact same kind of triangle, meaning instead of having x squared, if I have cosine squared, and then I also have sine squared, as long as that's the same triangle, so as long as that angle is the same angle, so theta is the same as theta, then no matter what, we're going to get a value of 1 out of that. So if I took like cosine of pi over 4 squared and I took sine of pi over 4 squared and I added them, I'm going to get 1. If I did it with pi over 6 or pi over 3 or 5 pi over 4 or 18 pi over 2, whatever, you're still going to square them and you're still going to get a value of 1, no matter what the angle is. That's our Pythagorean identity. Generally, we write this a little bit differently. Instead of writing the squared outside of a parentheses, we like to simplify it as cosine squared plus sine squared is equal to 1. Okay, this is one of the most important identities you will learn in this class. You will use this very frequently. In my class, this semester, second semester, in calculus, and things that you do after that. Cosine squared plus sine squared equals 1. Okay, there are actually multiple Pythagorean identities though, so I want to go through the other ones with you. So we're going to start with cosine squared plus sine squared equals 1. That's our most basic one. That's the most important one. If you have this memorized, you're going to be off to a good start. But we're going to come up with 2 more. The way we're going to come up with 2 more, and there's actually many, many more than a total of 3, but we're just going to come up with the basic 3, is I can take this equation and I can divide everything by cosine squared. So like underneath where you wrote the basic one, you'll notice I wrote it again so that I could show the divide by cosine squared. So have your basic one, box it, and then underneath that, write cosine squared plus sine squared equals 1, and then divide each of those things by cosine squared. We are going to now use our reciprocal and our quotient identities to come up with an additional Pythagorean identity. Okay, so cosine squared divided by cosine squared, Elijah, what would that be equal to? Cosine squared divided by cosine squared.
1.
Perfect. Harder question, Elijah. What would sine squared divided by cosine squared be equal to? Let me ask it differently first. What's sine divided by cosine, Elijah? What's sine divided by cosine?
Tangent.
Good.
Tangent.
What's the sine? So what would you get for sine squared divided by cosine squared?
Tangent squared.
That's it. You got it. Perfect. So a lot of guys will forget the squared here. It's still Pythag, so it still should be squared. And that's what happens when you have a sine squared over a cosine squared, you get a tangent squared. Okay, Elijah, last one. 1 over cosine squared. What do you think you get out of that?
Secant squared.
Perfect. Exactly right. So that's our second trig identity for Pythag is 1 plus tangent squared is equal to secant squared. I said there's 3 that we're going to focus on. So we're going to do another one. We're again going to start with our basics. Cosine squared plus sine squared equals 1. Instead of dividing by cosine squared this time, Justin Kruger, what do you think we're going to divide by?
Sine squared.
We're going to divide by sine squared. So not just sine, but we're going to take it and we're going to divide each thing by sine squared. Take a second, see if you can figure out what that is. You can look back at your other identities if you need to, if that's helpful. Carter, let's go to you. Cosine squared over sine squared. What's that equal to?
Cotangent.
Cotangent squared. Carter, we need to get you a new microphone or something because you're always a little glitchy sounding. What's sine squared over sine squared?
1.
1, correct. And then what's 1 over sine squared?
Cosecant squared.
Cosecant squared, unless you have some like robot filter on your mic. I think where it's time for a new microphone for you. Okay, I like the robot filter though. Cotangent squared plus 1 is equal to cosecant squared. Okay, those are our 3 basic identities. But like I said, we could arrange these differently. So another way I could write this second one would be if I, for example, took cosecant squared and I subtracted cotangent squared, then that would also equal 1. So it's not a new identity, but I could move stuff around, right? I could move things around and I could come up with a multitude of different identities here. Okay, we're just going to focus on those basic 3 for Pythag for now. Okay, but just be aware, anytime you have a trig function squared plus 1, or a trig function squared minus 1, or a trig function squared plus another function, or a trig function squared minus another trig function squared, all of that stuff might be Pythag. And so you might need to come back to these identities. Okay, any questions on any of these identities so far? We're going to do some practice problems with them. And you have a homework assignment due tonight. Okay, this problem says use identities to fully simplify each expression. Again, if you haven't yet, I do recommend reading 7.1 in your textbook. There's a bunch of examples in there. Reading it in your textbook, here's literally what I mean. Go through the examples. So go through the examples. It'll show you like step by step. You can click on it, like show answer or show solution. Your textbook's pretty great like that. I linked it in Canvas. So take a look and that might help you with some of these problems for tonight. So we have sine of negative x, cosine of negative x, cosecant of negative x. Those are being multiplied together. Okay. Now you might notice all of these have a negative x. So the first thing we're going to do is if they're even, we're going to simplify it, or if they're odd, we're going to simplify it. But we got to know which ones are even and odd. Landon, sine of negative x is the same as what?
Sine of negative x is the same as negative sine of x.
Perfect. So that's our first one. So we have negative sine of x. Landon, we're going to stick with you. Cosine of negative x is the same as what?
Negative cosine of x.
Not quite. Cosine is positive, or cosine is even, right? So what's cosine of negative x?
It's just cosine of x.
It's just regular cosine of x. Perfect. Okay, how about cosecant of negative x?
Cosecant is odd, so it's negative cosecant of x.
Perfect. Okay, excellent. So that's our first step that we could do to simplify this one. Again, this is like puzzles. So this is not us solving for anything yet. It's really just reworking this through the identities to see if we can simplify it and get somewhere else. Ryan Fury, what can you simplify from here? There's a couple options. There's one kind of maybe big one to notice algebraically. What can I simplify? So I have a negative in the front and I have a negative at cosecant x, right?
So if you draw one out.
So I have a negative sign times a cosine times a negative cosecant x. So I have a negative times a positive times another negative. What's that whole thing going to end up being?
Negative.
Positive.
Positive?
Should be positive, right? If I have like negative one times positive one times a negative one, two negatives make a positive, right? If it was three negatives, it would still be negative. So that means I can drop that out. I've got sine times cosine times cosecant. And make sure you have your x's on all of these. Otherwise, again, it is wrong. Everyone understand that we could drop that negative? We could have done this first. We could have done this later. Ryan, we're going to stick with you. Now, when we get to a point like this, it's not always obvious how to simplify. So I would suggest if you get stuck, always know that you can write every single trig function in terms of sine or cosine. Everything can be written in terms of sine or cosine. Okay, or both, right? Like tangent and cotangent, you would need both. But everything else you can write in terms of sine or cosine. So sine and cosine we're going to leave alone. How could I rewrite cosecant in terms of sine or cosine, Ryan?
1 over sine of x.
Fantastic job. So I have now sine of x times cosine of x, and then times 1 over sine of x. What identity is that you're using, Ryan?
Just the reciprocal.
Fantastic. Excellent job. So we're using our reciprocal identity on that one. So far we've used even and odd identities, and we've used our reciprocal identity. Adam, what can I do from here?
You can put sine x times cosine of x and then like put it over sine of x.
Sure, totally, right? Because I have a fraction here, I can rewrite it. You don't have to do that step. Like all of these are over 1. So you can cross cancel from here, but we can definitely write it as one fraction if that makes it easier to visualize, right? And so this is what he's saying, that we can write it like this. And then what would you do from here, Adam?
You cancel out the signs, so you only get cosine of x over 1. Which is cosine.
Exactly, which is just cosine. So that entire long, crazy thing to begin with just simplifies all the way down to cosine, right? So that's what we're trying to do. We're trying to take these very messy, crazy trig functions, and we're trying to see, is there any way we can use the identities to simplify them? That's why I said they're kind of like puzzles, because you're kind of just like unfolding and using different techniques to get them down to 1. Are there any questions on this first problem and some of the techniques we used?
Ms. Toshner, you were able to cancel out the negatives because they would have multiplied to a positive anyway, right?
That's correct. So that's what I did. Essentially, this is like -1 times sine times cosine times -1 times cosecant x. So I just took these two and multiplied them together, and I got a +1 out of that.
Okay.
Good question. Other questions? And we could have done that later, Dane. There's no reason to do it right then. Just seemed easier to get rid of it at that point, but we could have waited till the very end and then done it later. It would have been fine. Okay. Any other questions? All right, let's do another one. This one's a bit trickier. So we have cosecant of x plus cosine of x times cotangent of -x. I think someone is still unmuted, so just go ahead and check that you're muted. Julian, how would you like to start this one? A couple different things we could do to start.
You can probably start with the cotangent, like with the even odd thing.
Good. So how would you write that? So we're going to leave the cosecant alone first. So cosecant x stays plus cosine x stays. And then what's cotangent of -8x the same as, Julian?
Negative cotangent x.
Fantastic. Okay, so we can do that. This is still pretty messy. I don't see any pi over 2's minus x's. I don't see any, I don't know, Pythag in here. I don't have multiplication of things yet. I guess I could move that negative all the way out in front of that thing, right? So like positive cosine times negative cotangent. I could just, instead of having all of those extra signs, I could make this a minus here and do cosine times cotangent x. Does that make sense? Like I could just move that negative out in front. It's really cosine times -1 times cotangent. So I could just move that negative out in front. Okay. So this is a place where we might get stuck. Sam, any ideas of what we can do from here?
So I'm thinking we turn cotangent into, where is it? Actually, I don't know if that would work. It'd be 1 over tan theta. I'm kind of stuck, honestly.
Yeah, so this is a place where we normally get stuck. What we can always do if we get stuck, we can always write everything in terms of sine and cosine. Always. Anytime we're stuck, we can always write everything in terms of sine and cosine. So that would be my suggestion from here. So Sam, in terms of sine or cosine or both, what is cosecant of x the same as?
That is 1 over sine of theta.
Yeah, and sine of x in this case, since it's an x, right? So we can't switch our variables, so we have to use an x here in this case. Okay, cosine is just cosine. That's already in terms of sine or cosine. So what's cotangent? And so you had said before 1 over tangent, which is true, but we can even write it in terms of sine and cosine. So what's cotangent in terms of sine and cosine?
1 over sine of x over cosine of x.
So that's too many fractions. Go back to your quotient page. What did we say that cotangent was equal to?
Oh, right. Cosine of x over sine of x.
There we go. So it's because it's the reciprocal of tangent. If you know tangent, instead of doing 1 over, just flip the fraction, right? So if tangent sine over cosine, cotangent is cosine over sine. Okay, excellent. So we're here. And now we're going to try to see if we can do anything with this. So we have 1 over sine minus really cosine over 1, if that helps you to think about it that way. And then times cosine over sine. Oliver, can I rewrite this in any kind of way? What's this the same as?
She said she's not.
Would it be negative cosine squared of x over sine x?
That's perfect. So we have 1 over sine x still over here. And then Oliver said minus cosine squared of x over sine x. Exactly right, because this is really just like over 1, right? So we could multiply those together. Okay, Oliver, I have the same denominator there. I have a 1 over sine x, and then I have a minus a cosine squared over sine x. Since I have the same denominator, what can I do with that?
Can't you just, I mean, technically multiply by sine x, but like you can just kind of cancel it out and it's 1 minus cosine squared of x.
So we can't just randomly multiply. If I don't have like an equal sign, so I can't multiply. But if I had like 1/2 plus 3/2, if I have the same denominator, I can do what?
You can just make it 4 over 2. So 1 minus cosine squared of x over sine x.
Fantastic. Perfect. So since I have a common denominator, I can now combine it into one fraction. Okay, so here is where it gets a little tricky. I know this is a tricky one in general. But now I have like a cosine squared and a minus and a 1. So my brain says, hey, that might be Pythag. Anytime I've got squareds and 1s being added or subtracted, or squareds and other squareds being added or subtracted, I should come back to it might be Pythag. So when I say it might be Pythag, I'm going to literally write down basic Pythag first. Cosine squared plus sine squared equals 1. And I'm going to see, can I rearrange that equation in black to get a 1 minus cosine squared? Thomas, how could I arrange that equation in black to get a 1 minus cosine squared? Thomas, are you here?
I had to move out your camera so I could see it. So you would divide by cosine squared, right?
No, I want 1 minus cosine squared. So I have a 1 over here. How do I get a 1 minus cosine squared?
Oh, you just subtract cosine squared over.
I just subtract cosine squared from everything, right? So if I subtract cosine squared from both sides, everyone should be writing this down because this will help you get some right answers because it's not always this straightforward. Not that this is that straightforward, but you end up getting sine squared equals 1 minus cosine squared. So we're using our Pythag identity. Again, we noticed it could be Pythag because there's squareds and ones. And now what that says is 1 minus cosine squared, that's totally just the same as sine squared using that Pythag identity, right? So 1 minus cosine squared is equal to sine squared. So Thomas, how does that help me with my blue, where we left off in blue? So we had 1 minus cosine squared over sine of x. How can I rewrite that now?
You could just substitute 1 minus cosine squared x for sine squared.
Yeah, and it would be sine squared x in this case. Yeah, I just did a basic example with theta, but this problem has x's in it, so it's going to be sine squared x. Okay, exactly right. So we have sine squared x over sine x. What's that the same as?
That would just be sine x.
Fantastic job. And that would be as simple as we can get this one, right? So hopefully you're starting to see how this works like puzzles. Like, well, I don't know exactly where to go, but I know some of my identities. We recognize, oh, the negative x, that's an even and odd. And then, okay, I get stuck. So I'm going to change everything in terms of sine or cosine. And then, oh, I've got a common denominator. I'll put it together. Oh, that might be Pythag. Let's see if I can rearrange Pythag, and then things simplify. Okay, there are a lot of steps here. You have to stay very, very organized in order to solve these. Are there any questions on this problem so far? That would be our final answer. Are there any questions on this problem?
Yeah, I'm kind of confused on what you did from the 1 minus cosine squared x over sine x, and then what you did with the sine squared x over sine x.
Absolutely. So I went and I remembered our basic Pythag identity. I noticed that there was like ones and squareds. And if we go back to our Pythag identity, all of those had like ones and squareds of functions, right? So like cotangent squared plus 1, or 1 plus tangent squared, or our basic one had cosine squared and sine squared, and then there was a 1. So anytime you have those functions where they're squared and they're either like added to another function that's squared, or they're added or subtracted to 1, my brain goes, this could be Pythag. And that's where your brain will go as well. So at that point, when we had our 1 minus cosine squared, I went back and I wrote down our basic Pythag identity. Cosine squared plus sine squared equals 1. And then I just said, can I move that equation around at all? Can I do some basic algebra so that I can end up with 1 minus cosine squared? And so to do that, I could subtract the cosine squared to both sides. And I ended up just having a sine squared left. And so since I have sine squared is the same as 1 minus cosine squared, I could replace it. I could take 1 minus cosine squared, and that's exactly the same as sine squared. And then sine squared x over sine x is like sine times sine over sine. And then they simplified just down to a single sign. Does that make sense?
Yeah.
Awesome. Okay, excellent. Let's go on. Okay. Go ahead and write this down. I've switched it up. We're not using x's on this one. We're using thetas. So just make sure you're consistent with whatever I give you. So this is 3 sine cubed theta times cosecant of theta plus cosine squared of theta plus 2 cosine of negative theta times cosine of theta. Give you guys a second to write this down. Jorge, what can I do to start this one out?
So what I would do, well, since cosecant is the inverse of sine, I just start off there.
Reciprocal of sine, but
yeah,
yes.
Reciprocal.
Yeah, all good. I knew what you meant. Okay, so then what would you do with that?
So I turned that into 1 over sine theta.
Perfect. So we have 3 sine cubed times 1 over a sine of theta. I love it. Okay, what else? Just leave the rest alone for now.
Mm-hmm.
Perfect. Okay, so we've got plus cosine squared plus 2 cosine of negative theta times cosine of theta. Excellent job. That's a great first move. By the way, there's not one right way to get to the answer. So if you had a different first move, Jorge's first move is good. Your first move might be good. They might not be the same. Okay, Jorge, what can you do with that now that you've made that 1 over sine theta and it's times, or like there's really like a sine cubed over 1 over here? What can I do?
Well, you could multiply them together and then you could get 3 sine squared theta.
Fantastic job. So we can essentially cancel one of them out, right? We can cancel out the cubed and we're left with a sine. And then that cancels out this divide by sine over here. So we've got 3 sine squared plus cosine squared plus 2 cosine of negative theta times cosine of theta. I don't know why I randomly sometimes use parentheses and sometimes not. Okay, let's go to Ben. Ben, what else can I do?
Cosine negative theta. Cosine is an even function, so that's the same thing as just saying cosine theta. So you can rewrite it as
so I'll leave the front stuff alone. And then what does this become, Ben?
2 cosine theta.
Okay, Ben, what can we do from here? So I agree, it's even. So we don't get like a minus 2 here. Because cosine is even, that negative theta is the same as a regular theta. Okay, Ben, what else can I do? What do you notice?
Well, it could become 2 cosine squared theta.
Good. So we still have 3 sine squared theta plus cosine squared theta, and then plus 2 cosine squared theta. Okay, let's go to Aiden. Aiden, what can we do from here?
So you can add the 2 for the cosine squared theta and the 2 cosine squared theta and get 3 cosine squared theta.
Excellent. So we can add, we've got a 1 cosine squared and then a 2 cosine squared. So Aiden's exactly right. That'll give us a 3 cosine squared theta here plus a 3 sine squared theta. Aiden, what can I do after that?
You can take a 3 out and then you can.
Sorry that it sounds like you guys are getting announcements right now. We're not quite done, so I don't know why they're calling class early, but sounded like you said, we'll take a 3 out. We got sine squared plus a cosine squared left in there. And what's that, Aiden? What's sine squared plus cosine squared?
That's equal to 1.
That's equal to 1. So what's your final
answer? And then
answer?
you multiply by 3 and get 3.
So this whole long, messy, crazy, stupid thing, that whole thing is just equal to 3. That's how much it simplifies. Make sure you don't leave yet, guys, because we have to go to math together. Okay, that whole thing simplifies down to 3. So again, this is very much like puzzles. We're just reorganizing. We're using our trig identities. We're changing things in terms of sine and cosine. We're recognizing where those identities come into play. Okay, all right, so it's 9:50 now. So we are going to go ahead and I'm going to share my screen and we're going to do the prayer or the mass. So no one should be leaving the location they're in. I know it says if you're on Flex, go to the Great Hall. Elijah. No, because you're not on a Flex.
The dude from downstairs was yelling at us saying go to Great Hall. Because they had to pass up the Eucharist and stuff. And they don't pass it up us here.
Okay. All right. I don't understand that. I thought, okay, so if you're at home, then you'll stay on this call. If you are at school, it sounds like go to the Great Hall. Okay, if you're at school, go to the Great Hall. But if you're at home on this call, stay on this call.
Thank you, Ms. Dosher.
Have a great day, guys. Make sure you get your homework done tonight. Thanks, y'all.
Thank you.
Okay, so let me go ahead and find this and then share it with you guys. You probably also have a link, I'm guessing, but I'll find it and we'll just share it and we'll watch it all together.
Can I go to the restroom real quick, Ms. Dosher?
Yeah. If you guys need to go to the restroom, I don't think it starts for another like 5 minutes or so. So if you want to go now, go ahead. Or get a drink of water or a little snack or something.